Cool. Okay, guys, so we're just going to begin. Have I got the thumbs up to start? Yeah, awesome, great. So welcome to London, everyone. Before I begin, who's actually from London here? Raise your hand if you're from the area. That's about half the room, maybe 60%. That's really cool. So the rest are just from around the world. If you're from Italy, you know, you can just go outside as well. I'm only joking. Okay, so I also want to get another raise of hands. Who's done any Solidity programming before? Okay, so you're all quite familiar with it then, so maybe that's going to be too easy for you guys. Maybe I can try to make it a bit harder. So what I'm going to do first is I'm going to give a brief overview about smart contracts and Solidity, and then we're going to build a very simple contract that's a hello world, that's censorship resistant and can never be taken down by any nation state. You know, everyone likes a censorship resistant hello world. Okay, so
sorry,
yeah?
Before you start, I think there are some people in the room who weren't here earlier with the Wi-Fi, so is there anyone who needs Wi-Fi details? Okay, cool.
You only need Wi-Fi. So if you connect to the club quarters and type in the room number, 999, you can put any email address or name in and you'll automatically connect. So just one last time, look for club quarters on your Wi-Fi list, and the room is 999.
And then you can just put any last name.
Any last name, you know, you can put Satoshi Nakamoto, V Butter in if you want. We can all be V Butter in today. Cool. So what is a smart contract? Just to make sure everyone has, you know, a high-level view of what we're all, you know, what I think a smart contract is. So the first definition that was really released was from 1994 by Nick Szabo, which is a smart contract is a computerized transaction protocol that executes the terms of a contract. But for me, when I read this definition, it doesn't really make any sense to me, and I can't really process or compute it that well. So raise your hand if this makes any sense to anyone in this room. Cool, exactly. So a better way to think about it for me is that a smart contract is a trusted third party with public state. Public state means it doesn't keep any secrets whatsoever. If you give this trusted third party your date of birth, that date of birth will be visible to everyone in the world. Now the smart contract gives you some guarantees. First, when I deploy the third party, its code can never be modified, give or take how you design it. And if I want to call a function, let's say the vote function, it will always execute the code I expect. As in, if I call vote, it will run the vote function. You know, there's no hidden black box code there in most cases. And also, one of the safety features is that it will never stop halfway through. So if I call the vote function, it will either execute all the code, or it will stop and revert and not execute anything. So it's all or nothing. And of course, it likes to gossip, and it can't keep any secrets whatsoever. So that's the best way for me to think about a smart contract. I want a third party to coordinate some protocol or action or game, whatever, and all that third party is doing is really coordinating and making sure everyone in this room has the same set of code, and everyone here can execute the same code on the same state. And it's a cute little robot. Cool. Now on Ethereum, you have two types of accounts. The first is an externally owned account. That's your Ethereum address, and it's a public-private key pair. I have a private key on my computer, I can do digital signatures, and I can authorize transactions. And of course, the public key, the Ethereum account, is what I give you guys, and you can all send me money. Now, there's three different types of transactions on Ethereum. The first one's really straightforward, value transfer. I can sign a transaction where I can send anyone in this room some ETH. You know, that's sort of like just like Bitcoin in a sense. But then we can go a bit further. So we can create a contract. You know, creation transaction is what I call that, where in the transaction, in the payload, we put the bytecode of the contract. We deploy that to the network. Then this transaction will create the smart contract in its initial state. So everyone here can see that I created this smart contract, and everyone here can get a copy of the bytecode. And finally, an invocation transaction. If this is a voting contract that's on the blockchain, I sign a transaction where I say I want to call the vote function on this contract with these arguments. I sign that, I broadcast that to the network, and of course in that transaction we'll process the vote. Of course they all have the same transaction format, but in terms of the idea, there's three different types. Now on Ethereum, there's also this idea of gas. So who's heard of gas before? I guess I should really ask, who hasn't heard of gas before? Okay, everyone's, okay, one person, cool, cool. You don't have to really raise your hand if you don't want to. But on Ethereum, we have this idea of gas. Okay, so why do we have gas for? One of the issues is that when we send this transaction to the network, we're sending it to thousands of people in the world. We need to make sure that this transaction doesn't do a denial of service attack. It doesn't do a for loop 10 million times. We need some way to measure computation. We need some way to limit the amount of computation a single transaction can do. So we have a gas unit, and I'm going to explain that in a second, and there's a gas price. So one of the quirks of this network is that, let's just say I want to call the vote function. I need to sign a transaction, I need to broadcast that to the network, and I need to get that in the blockchain. Who puts it in the block? Miners. These guys solving that proof of work. So I need to set a gas price such that when the miner includes my transaction, they get rewarded a fee for doing this. Okay? So it's a bit like going to the gas station. For every gallon of gas I want, it costs us $1. And if I use 10 gallons, then the miner's going to get $10. Cool. So just as a very simple illustration of how gas works, remember, on the Ethereum virtual machine, at the end of the day, everything's assembly. There's opcodes that are executed, and every opcode has a fixed gas cost. So in this case, grabbing the timestamp will cost 10 gas. Now we're just going to run through a very simple example. Of course, this is not what opcodes look like in real life. This is a much prettier way to represent them. So in my single transaction, first what I'm going to do is fetch the timestamp and the hash for block 500. Now this will cost me 60 gas to run both of those opcodes, both of those steps in the execution. Now when I add them both together, I add the timestamp and the block hash, that'll cost me up to 65 gas. Then when I fetch the Coinbase transaction, I run out of gas. Coinbase required 50 gas, but my transaction had a gas limit of 80. So because of the gas limit, I can't finish this execution. So I go to fetch the Coinbase, it explodes, I get an out of gas exception, and everything rolls back. And that's exactly a good way to think about Ethereum transactions. If you don't allocate enough gas, then it's going to explode and not finish the execution. Cool. And finally, what does this look like on the network? So every 12 seconds, there's a new block. And in this example, I've created a smart contract, and the contract code is here, and it cost me up to 98,000 gas. Later on, blocks are created, and no one's using the smart contract. And then finally, Bob comes along, he signs a transaction, he broadcasts this to the network, and of course, he's going to call a function on the smart contract. So again, as an example, I've deployed the voting contract, and then over here, Bob may have casted a vote in my contract. And that's basically how it will be processed in the blockchain. Okay? So now what we're going to do is go through a very simple Solidity example of writing hello world. So I want everyone to go to this website, remix.ethereum.org. Okay? There's an online IDE where we can write simple code and test it out. Now what's important is that on this network, we have this Ethereum virtual machine. So all of the programs are executed in the Ethereum virtual machine. And finally, the most important thing to take away for Ethereum is that these programs will not do anything in the background for you. Normally when you write a program, you can have a task that's always running in the background. You can't do that on Ethereum. Your smart contracts won't do anything unless there's this transaction. Unless you send a transaction, that's the only time your contract will do any execution. So there's no idea of this background task. Everything's event-based. Cool. So now let's go into our remix example. And is there any questions before I continue, or is everyone quite happy with that? OK, cool. And remember, guys, this is a workshop, so ask as many questions as you want. There's no such thing as a stupid question. Cool. Oh, actually, there's one last thing I want to highlight. While you guys load up Remix, when I first discovered Solidity back in 2016, this is the first example you'll see on Remix, which is a ballot program. So in this very simple example, it's a simple voting contract. There's a list of proposals. So when I create the contract, where is the code for that? Well, I've deleted that. OK, so when you create the there it is. When you create the contract, you say, there's a certain number of proposals that I want to send. So maybe there's 3 proposals that people can vote on. So when I create it, I say there's 3 proposals, and all of this gets stored. Then over here, there's the vote function. So I want to vote for proposal 1. So what I'll do is I'll create a transaction where I say I want to go to this voting the ballot contract. I want to call the vote function, and I want to vote for proposal 1. I put that in, I broadcast it, and then it'll process the vote function. So that's the very first, that's the very first example I ever seen for Aetherium. And over the years, it's been updated on Solidity. Whoops. OK, cool. And also, one last note is when you write these smart contracts, they tend to have 40 lines of code, but they hold millions of dollars of assets. So if you are going to write smart contracts, I assume everyone here will at some point in their lives, you have to make sure you have an adversarial mindset. Because this 40-line code program will be deployed on this public network that anyone in the world can access. So if you have a single bug in your contract, it will get exploited by someone. So in this example was the first parody wallet hack in 2017 where they lost $32 million. And then this was the DAO hack where the DAO got drained of $55 million. So the DAO was this Kickstarter program. The idea was that we deploy this contract. Anyone in this room could donate funds, and then it has a big pocket of money. I guess a bit like Moloch DAO. Now later on, anyone here could submit a proposal. If that proposal gets enough votes, then it gets funded, and the proposal gets the funding. But that contract had a bug where the attacker was able to drain $55 million. And it's a very subtle bug that maybe we'll cover later. Now, one interesting thing was that while this black hat hacker was draining the funds, the Ethereum devs also discovered it, and they were also trying to drain the funds. So you have the hacker and the white hat hackers both draining the funds at the same time, trying to save the day. Then Parity Wallet got hacked again, and they lost around $280 million. And this was a guy by DevOps199. He accidentally killed it. But what was interesting there was that, yes, some people remember this then. So in this attack, what was quite interesting was that there was a central library contract. When we program, we write dependencies. We say, I want to import this code, and I want to run this code. So they had a library contract. And they had 50 wallet contracts that all depended on the library. The issue was that this library contract had a suicide function that anyone could call. So DevOps came along. He set himself as the owner. He then sent in a suicide command and destroyed the contract. And by destroying the library, he also froze all of the other wallets because the functionality no longer existed because the library was deleted. I mean, I have a whole range of talks around for attacks. But this is a big deal. You don't want anyone to make a T-shirt for your smart contract. OK? And that's really it. So when you do write these smart contracts in the future, please look online, read as many tutorials as you can on how to break smart contracts. Maybe we'll try to break one later if we have time. And last thing is, it's slow, expensive, and everyone has to share this resource. As you're going to see, smart contracts are very expensive to execute. So you want to minimize what you do in the smart contract and maximize what you do off-chain. You don't want to do everything in the smart contract. And that's it. So these are little links that I've made. So last year I taught yep, go ahead.
So when you kill the contract, where does the money go?
So in this example with the library, all the money was on the 50 contracts here. So every contract was a wallet. So you had a wallet contract 1, wallet contract 2, and you had the library. So when this library is destroyed, the money's still on the wallet contract. But the wallet contract has no functionality. So it's frozen. It's just stuck there, which must be so painful. I mean, if I were the victim of this, I'd just be really annoyed that I can see my money there, but I can't withdraw it.
But technically, the suicide does usually return to.
Yeah,
If you commit suicide, you give it an address, and it sends it all there, right? Or
yeah.
something like that.
Well, typically, but the library obviously didn't have money in this case. But normally, when you do destroy a contract, it sends the remaining funds somewhere else. Yeah, go ahead.
So if the contract is killed, can it be resurrected?
It depends on how you design it. So I think with create 2 opcode, you can do that. But obviously this wasn't predicted in time. So not yet, no. I mean, what you could do is you could hard fork the network and reinstate the contract. And I'd be a believer that you should do that. In this scenario, it's verifiable that the funds are locked, and it's verifiable that this was deleted. And by simply recreating it, you would withdraw the funds. I'm quite positive. I mean, I would opt into that, but a lot of people wouldn't, which is why it hasn't been done. Cool. Any other questions? OK, awesome. So what we're going to do now is we're going to run through this first tutorial. So if you want to type in those links, each of these, so what I did last year was I taught a master's course in MSc on cryptocurrencies. And these were the tutorials that I gave to the students. So they're quite in-depth in terms of a lot of the constructs that you can do in Solidity and how to break smart contracts. But we'll just run through the first one for now. So you don't really have to open it, but I'll send these links later on, and you can look through the tutorials if you want. You know, they get incrementally harder. So, so with the remix I'm doing now, if you find this too easy, then you can just jump ahead to this one and do this yourself right away. This is probably the hardest one. And I don't think anyone will get that done in 20 minutes. Cool. So let's just go through the hello world example. So now I can sit down and go on remix. Whoops. OK, cool. So this is the remix IDE. OK, so what we're going to do is create a new smart contract. So if you go up here to the top left, you'll see a little plus button. You just click that. OK, top left, little plus button. And then we can type in the name of the new file. So we're going to call this hello world.so. Keep an eye on time. Awesome. OK, so again, top left, hit the little plus button. And then you can call your contract whatever you want. But I'm going to call it hello world.sol. Cool. So you'll notice when you open this new file, your first error message will appear. Which is basically telling, you need to be able to inform Remix, or whatever compiler you're using, what version of Solidity you want to use. So in this case, we just type in pragma solidity, and I'm going to make the text bigger now, 0.6.1. So how do I zoom in? Oh. See, that's how you tell I'm an old man. I don't know the shortcuts. Cool. OK, so the first thing you do is tell Remix what version of Solidity you want to use. So we just type in pragma solidity version 0.6.1. I always forget to do this, then I always get the error message. OK, and then next what we're going to do is define our smart contract. So we're going to call it contract hello world curly bracket curly bracket. Then I'll just wait a few seconds because I can see people are typing and catching up. Awesome. So now what we're going to do is, the whole point of this hello world is that we want to tell the world, you know, hello. So what we're going to do is first define an event, which would be, we're going to call it event message. And this is going to take a string, which would be another message. So what's really nice about Aetherium is that when I call a function in a smart contract, you can create events. OK, so if I watch a smart contract, I'm just watching it, and I want to figure out when some cool event happens. As you're going to see, when you call a function in the contract, you can make the program emit a message to the outside world to notify the outside world that something cool happened. And that's the whole point of an event. It makes it really easy for anyone watching the smart contract to be notified when something happens. So what we're going to notify the world about is to say hello for now. OK? So now what we're going to do is create a function called send message. And it doesn't take any parameters for now. OK? So we're going to define a function called send message. Now, you'll notice one aspect here is that we have the keyword public. So when I deploy this smart contract to the world, I send it into the blockchain, I have to define a function to either be internal, so no one can execute this except the smart contract, or public. If it's a public function, then anyone here can execute the function. So if you're familiar with Java or JavaScript, this is probably quite similar. Some functions can only be executed by the program. Other functions can be executed by anyone. It's external API. So here we use public to say it's accessible by anyone. And then what we're going to do is emit the event message. And for now, we're just going to hard code it to say hello world. Whoops. Cool. So obviously, it's a really boring program. But of course, it's censorship resistant, and no one can take this down, because we're all cypherpunks. So now that we've written this code, I'm just going to print this out a bit. Now what we want to do is deploy it, run the function, and then we can emit hello world to the world. So we'll go to the Solidity Compiler, which is this one. It should be the second menu down. Can everyone see that, by the way? Because sometimes Remix is a bit... Can I see your example? Sometimes Remix doesn't set this up. Yep, I thought so. Cool. OK. So guys, if you don't have the compile option, go to the little plug down here, the plugin manager. Now what we're going to do is activate the Solidity Compiler and activate deploy and run transactions. So there's a second option, bottom option. So just to repeat, go to the little plug, the plugin manager, activate deploy and run transactions, activate Solidity Compiler. You can ignore the rest. I never use the rest. OK. So now we go to the compiler. So what you should see is that it should auto-compile and already be compiled. But I always click this to be double sure, because I don't trust auto-compile. I've run into some troubles in the past. OK. And now we click on is deploy and run transactions. So can everyone see this on their screen? Raise your hand if you cannot see this on your laptop, down there. Mary, can you help the guy behind you? Just because you're there. Awesome. OK, so can everyone see this on their laptops? Nope. Chris, can you help that guy there? The guy in the blue top. Cool. And OK. Can anyone else not see this? Are you OK? Yep. Let me just jump down quickly. So all my helpers are gone.
Sorry, missed a step.
Just click that one.
Which one?
Oh, click compile up there. Down.
Yeah.
Hit compile hello world.
OK.
See, exactly. That's why we don't trust the auto-compiler. My point proven. Cool. OK. So guys, what we're going to do now is we're going to deploy hello world. So we have to click deploy. Bam.
The default gas limit?
Yeah, just use the so the default gas limit for this transaction is 3 million gas. But our contract will actually cost in practice. Let me see how much this actually costs. Costs about 100K gas. So I'll go through that now, actually. So guys, hit deploy. Everyone click the word deploy and just click it once. Now, when you go to the bottom right-hand side down here, you'll see a transaction in the VM. And it should have a big green tick. If it doesn't have a big green tick, raise your hand, because then something went wrong. OK, has everyone got a big green tick there? Cool. So click it. And we can get cool information about this transaction. Oh, you guys OK? Oh, OK, awesome. Cool, cool. It works. So you'll notice that this is from a certain address. That's you, because you signed the transaction and you broadcast it. And we've sent it to the hello world constructor. Basically, we've created the smart contract, so there's a new address for the smart contract. I allocated 3 million gas for this transaction. That was the maximum quantity of computation I was willing to pay for. I was willing to pay up to 3 million gas. I only used 100,000 gas, give or take. And you'll see down here that, well, there's nothing interesting yet. But we can all see that the contract's created. So if you scroll here to deployed contracts just here, click the little right arrow next to it. OK? And you'll see the function send message. OK? So again, go to the left-hand side, go to deployed contracts, click the little arrow, and you'll see the list of functions. OK? So has anyone not got to this part yet? Raise your hand if you're not here yet. Cool. Everyone's here. So all we have to do is click send message. Bam. You know, it's like click bang, you know, the dirt is gone. And now we've sent the transaction to the network, and we should hopefully have emitted the word hello world. So click the transaction, scroll down to the bottom, and we'll see in the logs that there was an event called message. So we've notified the world that there was a hello message, and the message was hello world. And so everyone here is now emitted and notified the world of hello. OK, so just one last time. In the logs, you'll find a transaction with hello world.sendMessage. OK, we click it, we scroll down, and we can see the event. Now, this is obviously a really useful feature for more than just hello world. If your contract's doing anything interesting whatsoever, please emit an event, because it makes it really easy for anyone watching your contract to watch for interesting events and to do something in response to this. But the issue is that hello world's a bit boring. It would be really nice if we could send more than just hello world. So let's go back to our contract. OK?
So what's this topic?
Oh, topic. Where is it?
About the event.
I don't really know the best way to describe that. I think that's just the. How would you guys describe the purpose of topic?
It's a hash of the event.
OK.
You go to collect the events.
Oh yeah, OK. It's a hash of the word event and parameters. Yeah. OK, I always forget. So when you're working, OK. So basically, the point of topic is that when you're writing code in Web3 and you want to watch for an event, you normally say, this is the event I want to watch for. So that's just a hash of the word, of the string, event and the parameters. Cool. Yep.
When you say it's a hash for everything in those tags, is the meaning for the Markov trees in the blockchain?
So in Aetherium, OK, so where do events live? Let me get to that first. So in Aetherium, every transaction will produce a receipt. The output, the finished execution, and what we care about. The event lives in the receipt. So in the blockchain itself, there's no record of the event. We don't store the event. When we execute the transaction, we get a receipt, and we get the event data there. Now in Aetherium as well, in the block header, there is a Merkle tree of all the transaction receipts. So you can verify yourself that this transaction receipt actually exists for this block, for this transaction. So there's a commitment to it, yeah. Cool. OK, so any other questions before I continue? Oh, OK, yep, go ahead.
So this emits also costs gas? Or?
Yes, it costs, I forget how much costs exactly. It's not too expensive. Let's say 1,000 for now, but we can Google it. Yeah?
I know that the function can also just return a value instead of emitting event.
Yep.
If it's a transaction, can you actually get the result of that value? Or
Not very easily.
You always have to emit an event?
Events are much easier. So normally when you run the transaction, the whole point of the return statement is to return to another smart contract or to another function. It's very, very, very difficult to get it out. So hard that I would even bother trying.
And one good point is smart contracts can't read these events. Like you said,
Yeah.
the event is in the history or in the receipt.
Yeah.
One smart contract can't go read some event and then.
Yeah, that's a very important point, just to reiterate that. So events are only for humans. in meat space for you and I. They are not for other smart contracts. If contract A is calling contract B, you return a value to that. So what you would normally do is returns. In this case, we're going to return a string. And we'll return, return hello world. And let's just put this in now. OK. We need to do memory. Cool. OK, cool. Yep.
What's the memory for?
So memory means that this variable will only exist for this transaction. It's not stored for long term. And actually, there's some subtle attack factors. I mean, not attack factors, subtle bugs if you mix up stories in memory. If I get time after the next tutorial, we can go through one of the bugs. It's in one of the tutorial sheets. If you look at tutorial 2, I think it's in there of how you can mix that up. Yep.
Where the exactly message is getting stored?
What one?
The message, hello world.
So this is hard-coded in the bytecode. So when I deploy the contract, it is hard-coded in the program right now. And that's on the blockchain.
But is it not in the hash format?
The hash format. So this, you mean this hello world here? So this is just a program. So there'll be bytecode, and that bytecode will live on the blockchain. So hello world is hard-coded into the program. Yeah. So what? Yeah.
So when I look at the API that gets posted on like a certified contract on like Etherscan,
Yeah.
and it says this method returns this value.
Yep.
Is it actually for a transaction function? Is the API actually saying this function is just emitting an event? And
If it says return, is that for event? I'm pretty sure it's just for returns. So if it says returns, it'll just be this statement here, effectively, equivalent. So it shouldn't. I don't think the API should say what event is there, but I don't remember.
So the API, okay, so the API doesn't say what events are being emitted on method.
I don't, Chris. What? No, I don't think it does. No, yeah, it doesn't. So the returns just means that this function will return a value, but again, that's only useful for other smart contracts. Yeah. And that's important. So the reason for that is if there's a contract surviving on the blockchain, that says an Oracle service, I want to interact with that Oracle. So I need to know the return statement for that. So I look at the API, I see the function, I see the return statement, then I can write a contract that will match that. That's one of the purposes why you would have that. Again, it's for contract space. OK, any other questions? Yep.
That event, is that public?
Yes.
It can be called from outside the smart contract.
So if you want to play with this will live on the blockchain, and you have to send a transaction to the network that invokes this function.
That invokes send message?
Yep. And then anyone can read it.
So you can't send a transaction that invokes message. That invokes, message.
Message. Oh, not the event, no. No, you can't just call the event, yeah. Not that I know of.
Here in the ABI.
The events?
Yeah.
I don't think events are in the ABI.
Maybe because people are
Go ahead.
Take a look at it.
Yeah.
Release status to the API.
Where is the ABI? I don't think I've ever looked at the ABI on Remix before.
Consumers have to.
The compiler. Yes.
In the compiler, that's C.
Yeah. The API.
Oh, ABI, I've never used this feature. Here we go.
Yeah. So we're gonna.
Oh, it's just copied it.
Someplace.
Of course, that's C.
I'll find it.
Oh, okay, there it is. Oh, I didn't know that.
But it's not for calling, it's just for people
Yeah.
listening.
It's just saying that the event exists. Thank you for that. This shows you how often I look at APIs. There you go, awesome.
Somebody executes that function? Like as a log record?
Yeah.
Yes, okay.
Cool. Okay, so awesome. I learned something new. Good job, guys. Okay, so now I'm going to quickly move on to one more task, and then I'll give it over to the builder crew to go through the debugging. Okay, so what I want to do now is allow anyone in the world to set a message and emit it. Okay, it's a bit like a bulletin board or a broadcaster. So this is really easy to do. It's just like any programming. We're going to give an argument or a parameter. So we're going to do string, message, and of course again we have to put memory in there. So this will only exist for this function call. and then we put message in. Okay, and again, we're just going, we'll just keep hard-coded hello world in there. Why not? That's fun. Okay, so we're just going to modify the function, add in a new parameter called message with a type string. And then we're going to modify the event and put message in there. Okay, very simple, very straightforward. So now what we're going to do is, again, we're going to compile it, make sure it compiles. Now, in this list, in deploy and run, that menu, make sure you delete the old contract. So go to the old contract here and click the little bin. Make sure you delete that, just to avoid running old code. That's normally a source of mistakes, and I've done that plenty of times. And then we want to redeploy the contract. Okay. Now that we've redeployed it, we actually have an option now to include a message. Okay, so we're just going to include a message to say, this tutorial rocks, because it rocks so much. And then we're going to hit send message and send that again to your virtual network. Bam. If we scroll down, we'll click here, and we'll all see that this tutorial rocks. So now we can enter in a random message, and that'll always be emitted. Is there any questions? Yep.
Yeah. When you deploy a contract, you get the address where you're going to test and deploy.
Yep.
Could you choose this address? How does it work?
So there's two ways to create a contract address. The first one is typically based, so they tend to be deterministic. So the first one is based on your address and the transaction nonce, so you don't really have much control there. The other one is based on, I believe, also the sender's address and the bytecode. Does that include the message?
Doesn't include the sender.
Doesn't it? OK, I think that was one of the proposals.
The init code and the salt.
OK, and a salt. Oh, yeah. So it's just the init code and a salt value next to it. So there you have a lot more control. It can be more deterministic. Cool.
This address has to be empty. I mean,
So I believe in the transaction field it will be empty. I don't think you actually fill that until the contract's created. Yeah, but you could double check the code. From what I remember, there was that you send it to, when you first create the contract, the transaction won't have the address in the field. From what I remember. Yeah, damn, this is bringing back like 3 years of memory. I just take this for granted now. Is there any other questions at this point? So has everyone completed this part of the tutorial? OK, what are you stuck on?
It says public returns.
Yep.
And string memories at the end.
Yep, that's it. That's the end.
And then we delete the old one? Or?
Oh, the old contract.
Yeah.
Yep, delete the old contract. Hit that little bin.
Yeah.
Make sure that's deleted. Because that, Yep.
And that's it.
Yep, and then you can deploy it again. So you can redeploy it and fill in the message to say this tutorial rocks. OK.
Why do you have to put in a memory keyword?
So a string is actually, it could be an arbitrary size of bytes. So because it'd be an arbitrary size of bytes, we typically just say this will exist for this function. So it's not like a native primitive. Native primitives, you don't have to worry about memory. But if you look at the tutorials are very in-depth. They'll explain the difference between storage and memory, and some of the bugs that would occur if you get them confused. OK, so I'm going to do one last task, because I think I have about 2 or 3 minutes left. So the only problem with this smart contract now is that it doesn't record any history. It will always emit a message and not keep any storage or memory around. So what we're going to try to do is keep a log of all previous messages. So I've got to remember how to do this myself. So we do this, string array, and there's old messages. OK. I'm pretty sure, where did I put public? I think it's here. Nope, didn't like that. Cool. OK, so in the code, we're going to create a string array that's denominated by the little curly, no, the, what do you call them, square brackets, we're going to make it public just so it's a publicly accessible variable and anyone can read it. And we're going to call it old messages. OK? And then here what we're going to do, and I hope this works because I haven't done this in a while, push message. Cool. OK? Now what's important is that because this is in storage, is a dynamic array. You know, there's no fixed size to it. It could be any size. OK? So just add in that new variable, string array, public old messages, and you can also do .push. I see people typing, so I'll wait a second.
So in this case, it's also variable, the size of the string, the array of string?
Yep.
You don't need memory?
Yep, exactly. It's variable size string. Yep. So under the hood, Solidity takes care of, you know, making sure there's enough bytes 32s. Because I think that's only a recent feature. I think it's only in the past year or two that they've had string. I remember when I started, they didn't have a string, and it was really difficult. OK, so I think everyone stopped typing now. So again, what we're going to do is we're going to make sure this is compiled. We're then going to go into deploy and run, delete the old contract. You know, always make sure that's deleted and this is empty. And we're going to redeploy the contract. You know, bam. Then we're going to scroll down here. And now you're going to see two fields. First is the send message function, where again we can put in any message we want. So we're going to say if London is going to be great fun. And we can send that to the network. You know, bam, sent. So if we just scroll down for a second, we'll see the latest transaction. We can click it. OK, and we can clearly see here that ETHLondon is going to be great fun. Now, what is important is that this is the very first item in the list. You know, we've actually stored something now on the network. So if we go to old messages, you'll see that this is blue. So from what I remember, a blue means it's not going to be a transaction. It will be a call. What I mean by a call is that I've got a local copy of the contract. I've got the local state, you know, because I've got the blockchain. I can simply read from it. So I'll do a .call, and I'll read from the contract. I can also do a .call that run the function locally to make sure it does what I expect before I send it out to the network. So .call allows me to run a function locally and not on the network. So what I always recommend is that when you actually write your smart contract in your Web3, I typically run the code first before I send a transaction out. So I want to make sure it's doing what I expect. So if we put in 0 here, the first entry in the list, we do old messages, bam, we get the string. It was stored on the network. If I put in 1, it should hopefully blow up. Yeah, it didn't change at all. Terrible error message remix. Invalid opcode, there you go, invalid opcode. Such a good error message. But I think everyone gets, yep, go ahead.
Just a clarification on the .call.
Yep.
Method. You say it runs locally.
Yep.
It can't do these state changes, or .call can't do these state changes.
No.
Right?
No, because you're not interacting with the network. It's just local between you and your blockchain.
But you can run through the state changes and make sure they're going to succeed.
No, yeah, exactly, yeah. Yeah. So the motivation is that you run the function first, and you can verify, yep, that's definitely going to cast my vote. It's not going to fail, and then you broadcast that out to the network. So you make sure that it works first. Of course, there's also another. I could do another talk about breaking smart contracts, and there's some subtle bugs around unpredictable execution. Go ahead.
Yeah, I have a question about the receipt. Like we see what
Yep.
the events the functions emit, but is there also a way to see what is changing in the storage in the state on the receipt? Which changes did the transaction make?
So I don't know how easy this is to access, but technically in the block header, there is what is it under? Maybe it's under this. There's a commitment to the entire state So in a block header, there's a commitment to the new state of the network. But I do believe that there's a commitment between every previous state for a transaction and every post state. So you can actually look up the state difference in the commitments for that. But an easier way is just to read the contract yourself.
And we include the old message array that changed. We include that.
It will, but I don't think it's going to be an easy to read format. I don't think it's very easy. I don't think there's given what's in the block header, I don't think it's as straightforward to work out the difference. I mean, obviously you can see the byte difference, but my advice would be just to read the contract. I mean, actually just do a local call and look at what's up. Yeah?
What's some good use cases for a dynamic array?
For what?
For a dynamic array, just because they can get very large and expensive, especially if
Exactly, they can get large and expensive, and there's some very, very subtle attacks around that. So, I mean, the motivation is that, I mean, I never use dynamic arrays, but the motivation is that, there's some item you want to add to a list. So one example could be a lottery. You want to append a new lottery ticket to the list. And then at the end of the lottery, I just tell the smart contract, my lottery ticket was 50, entry 50, and then the contract can look that up. Yeah, exactly, yeah. You should delete it over time. So one of the subtle attacks is that you could have a for loop here. So what we could do is for u and I equals 0, I is less than o messages dot length, I plus plus, and then we could actually omit every old message. And you don't have to type this in, this is just for fun. Now, can anyone tell me what would go wrong here except for my error message because I misspelled it? Can anyone tell me the issue with this function, with this for loop? It will consume a lot of gas. So if this list has, let's say, 50,000 elements, then actually the issue is that I call the send function, I run through the code, I get the here, I run this 50,000 times, I run out of gas. And what happens if you run out of gas? Everything reverts. If everything reverts, you can never finish this function execution. So you actually break the function. So dynamic arrays are really dangerous, and never do a for loop around a dynamic array. That's one of the subtle attack vectors. I mean, I could go on for hours with subtle attack vectors, but that's one of them. Any other questions? Yep.
Do strings have a fixed size then?
No, strings are just as big as they can be as far as I'm aware. I don't think there's any upper limit, except for the gas. Any other questions? Cool. Yep.
So let's say you want to know all the messages, and you don't want to use that loop for the reason you just mentioned.
Yep.
How can you gather them all using the emits that we have in the receipt?
So I think here is that, well, this is going to be one of the limitations, is that if you have an array of 50,000 elements, you probably never want to grab everything at once, because it's just too expensive computationally. What people tend to do is use mappings. So this is technically like a mapping, I can access a variable. So what you could do is say, function, let's say, emit old message, and then we actually put a uint in there. Okay, I. And then what we do is we just emit this. This is like, so what you would do then is just do it individually. So every new function would emit this old message. So you can still access everything, but you just never try to grab everything in a dynamic array.
You don't usually do it, but you could set up linked lists and you can parse through them and you can watch how much gas you have left.
You can do that, yeah.
Stop once you're getting close to running out of gas, and then do the next part in like another transaction.
Yeah, I actually did that in my old voting contract years ago. So the idea there is that you got to have a function that keeps. So basically, in a Solidity, what you can access is what is that opcode? It's gas used, gas left. That's it. Good. They made a special keyword. So you can actually check how much gas is left in the transaction. So you can say if gas is left is greater than 50,000, continue. I could actually just do it now. So let's just say we have a uint here, checkpoint. Okay. So what we do is that we go through for uint I equals 0, I is less than.
I don't think I've seen a single production contract that does that though. Right?
No, I would never do this. This is just me doing this for fun now. It's like, oh, messages, I plus 1. So you could have a function like this, for example, okay, where you just save the checkpoint. Else checkpoint equal I. Then you just stop. So we'll look a bit like that. But please never do this in production. If you do, you've never taken this class. But yeah, you could do something like that. Then you could keep recalling that function and eventually get over all the elements. Although that's all full of error messages, so it's broken. Go ahead.
What about, could you do things in batches? So you say, like, I want to just run 1,000 elements at a time, and then keep calling it until you...
Yeah, that's basically this idea here. But this is like arbitrary number. So what happens is that you'll go in this function. I should really fix this, shouldn't I? That's annoying me. So the idea is that in this function, you call it, it'll start as 0, because this begins with 0. And it'll start going through every element in the list. And every time it tries to, it'll do emit message, all messages, I. Why is this complaining? Oh, oops. Yep, there you go, camel case. Chris is probably laughing right now because I never do camel case. Okay, cool. Let's get rid of that. I'm done with this. Okay, so what you'll see here is that you go in, you'll call this function. It'll start from I. It'll then start looping through. Do I still have gas left? Yep. Emit a message. Gas left. Emit a message. Eventually, you'll run low on gas, and it'll just store the checkpoint and finish. You could even do a return there, actually. You just have a return there.
And the emitting of the message costs 50,000 gas, right?
This is like an arbitrary number. Normally, that's like 5,000. It's very small. It's like 2 or 5,000. It's not very big. That could be 10,000. Actually, that needs to be 30,000 because you're storing something. But yeah, that'll be the idea. You leave enough gas left over to store the checkpoint and then return. But please never do this. No, please don't. This is for fun. This is a really good example to highlight gas and the limitation of making sure you have enough gas left. So this is only for that purpose. Never ever. If you ever write production code like this.
But the for also uses gas, so we have
Yep.
to incorporate it into your.
Yep, exactly. Everything here causes gas. So normally if you get to this point though, you'll just save the checkpoint and return. So you have 30,000 gas to do this, giving that requirement. Yep. Oh yeah, awesome. So now we're done. So we're going to move on to the builder tasks. So just jump on up, guys. Yay. Cool. Do you need this?
So the idea of this session is to help you get a complete development environment for smart contracts and dApps. And everything is contained in this repository. And everything that I'm going to explain is here written in the repository. So if you want to go deeper into something, or if you miss some part of it, or you think that something is too easy for you, you can just skip parts of it, go there, and read it by yourself. So the first thing that we need to do is clone this repository and install it. Can you read this? Is it big enough? OK, so I already cloned the repository, but you have to do that. Like, it's a normal repository on GitHub. Go here, copy this URL, git clone, paste it, enter, that's it. And then to install this, you just have to type npm install. It may take a few minutes, so let's wait for everyone to install it.
Does everyone have the URL?
So let's go back to the URL. Yep. Sorry, can yeah, it's npm install. So, yeah, you need to install Node.js. So if you don't have Node.js installed or this npm install fails, you can go to this section on the repository that says development environment setup. And there you can go to this other repository that will teach you how to install everything. You can just copy and paste these things from the other repository to check if everything is already installed. Just paste them. And if everything goes well, you should, yeah.
What version of Node are you using?
I'm using Node 10.
Okay.
But then,
is that the best one to go with for this kind of
I would do that because it's the current LTS version.
Okay.
So I would go with 10, but 12 or 13 should also work.
Yeah, 12 breaks a lot for me because of Git.
Okay, yeah. So if you go to this other repository that it's linked on the installation section of the one I linked, there's instructions to install Node GYP.
Okay, thank you.
But I wouldn't recommend using Node 12. I would use Node 10.
Okay.
Yeah. Okay, has everyone installed this repository?
We can raise hands for those who have the dev environment ready.
Shall,
A few more minutes.
okay, let's wait 1 or 2 more minutes. What? Can you?
Is it executable for NPM?
NPM install. NPM is Node Package Manager. Yeah. So most tools from the Ethereum development ecosystem are based on Node.js. So even if you don't like using Node, you will probably be using it because that's what most people use. You can use another platforms and languages, but you'll probably be better with Node.js as there are more tools and more things to use. Fran, ¿llevas acá?
There is some kind of problem with the front end.
With the front end? There's a small front end here. We won't go very deep into that during this session, but you can see a small front end.
You use their like imports.
Yeah.
The browser doesn't.
Doesn't it? I mean, you have to run npm run dev in the front end, which will start parcel bundler. Shall I enter?
Yeah, but she didn't get it. She
Fine. Okay, shall we continue? Yeah. Okay, so we are going to be using a bunch of tools on this setup. The main one is called Bidler, which is a task runner and a development network. What does it mean? Like, with Bidler, you can do most of the things you need to compile and test and debug your smart contacts. So if we run npx Bidler help, Bidler will be executed, and you see all the options, all the things that you can do with it. So if we want to, for example, compile our smart contacts, we just run npx Bidler compile. Oops, compile. And that's it. I have already compiled them, so nothing happened. Let's do some Bidler clean. And compile them. OK. So Bidler has everything you need to test your smart contacts. Just like Remix from the other tutorial, Bidler has its own testing blockchain. So whenever you run your test, it starts up a new blockchain where your smart contacts are going to be deployed and executed, and you are going to be testing them from outside the blockchain in JavaScript. Is everyone familiar with JavaScript? Raise your hand if you are with JavaScript. OK, so normally you're going to test your smart contacts from JavaScript, and what it's going to happen is that you are going to use an Aetherium library to connect to the Ethereum network. In this case, this library is called Ether.js. With Ethers, you are going to model your smart contacts in JavaScript and interact with them through them. So let's see a small example of this. Go to the test folder, create a new file, example.js. And here you can write your test using Mocha and Chai. Does everyone know, or raise your hand if you know what Mocha and Chai are? OK, so less than half of it. Mocha is just a test runner for JavaScript. It's not something Ethereum related. It's like a super popular JavaScript project, which is very easy to use. You just have to write these describe methods. Where you declare your test like this. Describe is just like a section of your test. Should do something. So with describe, you just declare a section of test, like a bundle of tests that you are going to run. And with it, you declare one test. You just have to provide a title and a function that will test anything you want. And Chai is just an assertion library that you are going to use to actually test things. So you use it like this. Expect something to be equal to something else. And to run the test, you just run npx Bidler test. There's a whole bunch of tests running here, but the ones that we just created is here. Something should do something. Is anyone here? Are you following me?
Go back to the code.
Yep. 1. So 1 is any value we want. So let's say that here it's ASD, and we rerun this test, and as we are expecting it to be 1, like ASD should be equal to 1, this test will fail, and we'll see it here. So assertion error expecting ASD to equal 1. Right? So this is just a JavaScript test. It has nothing to do with Ethereum so far. So let's do something with Ethereum. This repository already has a simple smart contract. It's pretty much the same idea that Patrick explained, like a poll where there is a bunch of proposals and people can vote for them. And that's pretty much it. The only difference is that here you have an owner, which is, you don't have to read this whole thing. We're just going to go through it. So in this smart contract, you have an owner, that it's the person who deployed it, who's going to be able to add proposals, start the poll, and close it. So when you deploy this contract, the owner will be automatically assigned to the deployer. And the name of the poll will be stored. And our state variable is open, will be set as false. So let's test that that works from JavaScript. So this describe, we'll use it to test the poll contract. And we want to test that it should deploy correctly. What we are going to do is to get a JavaScript model of that contract. And we do it this way. Remember that everything here is written down in the README, so you can go as many times as you want through this, and also you can ask us about this on the Discord. Okay. So this is how we get a contract factory. A contract factory is just a JavaScript object that lets us deploy a contract. We are using ethers here to get the factory.
Ethers is ethers.js?
Yeah, ethers.js. Yep.
I don't see you imported ETHLondonUK.
No.
Injected by the.
It's already injected by Bidler. Yeah.
Okay. And the question is, how does ETHLondonUK find all the contracts? It's similar to the artifacts of.
Yeah, pretty similar.
Shuffle. Okay.
Yeah. Yep.
What's the difference between ETHLJS and Web3.js?
Well, I mean, both of them are Ethereum libraries. You can use any of them for exactly the same things. I think ETHLJS is like better for this kind of projects, like a hackathon project. It will bring you less problems, probably, and it's very documented. So that's why I chose Ethers for this occasion. You can use both with Bidler because it has a very modular architecture, and Ethers is just like a plugin in Bidler. And you also have Web3 plugins. But it's pretty much the same. Yep.
testing in JavaScript, one thing I've never understood with these kind of tests is like, describe is coming from where? It's you're obviously not importing it.
Yeah.
It's coming from some context that's being injected by the test runner.
Yeah, Mocha injects describe and it.
Okay, and then so ethers, does that need to be brought in, or?
You can.
Or is it in the context already?
It's already like in the global context. You can import it explicitly if you want, but just for brevity, I'm not doing it here.
Okay, so everything, all packages that are brought in as dependencies are in the global context, or is there?
No, not all of them. This is Bidler that it's injecting these things.
Oh, okay.
Yeah.
Okay, cool, got it.
Yeah. Okay, so now that we have this poll contact factory, we can just do deploy to get a new poll. Yep.
So is this testing deploys to the blockchain?
Yeah, but it's like its own blockchain. So yeah. No, the contacts get compiled before running the test.
Right, and so
This line just loads the compilation output.
that's what you test.
Yeah. Yep.
So behind the scenes, you use Truffle to deploy
No, we are using. No, I mean you could, but that's another set of libraries of tools. We are using Bidler and Bidler EVM here. Bidler EVM is like the testing library blockchain.
Truffle stuff.
Yeah.
Got it. So that it's not just in test.
Yeah.
I got curious. How do you say to the ethers that say, "Oh, get contract and pull"? He goes to the smart contract directory and read the smart contract. No?
It goes to the compilation output.
Yeah. How they figure out? Oh, go there and pull the how they get the
Okay.
line files.
¿Cómo sabe dónde están los artifacts?
There's like a default path to look for those artifacts, but you can set any path that you want.
So I need to write the smart contract at the same name of the contract factory, right?
Right.
Okay. So
yeah.
One question. So this just test if the contract can be deployed, that your functionality is like as supposed as you wrote it,
Right.
or it actually deploys it?
It actually deploys it.
So you misuse the test framework kind of to deploy your contract, right?
Right. Then you can use the exact same things to actually deploy it to mainnet.
So why don't you just write a script and run the script? Like why do you need the Chai framework here?
Wait. Just because it's easier, like Chai, because it's easier. You could just do that without Chai, but it has like a very nice API to test things. What you do need is a testing network, and that's the main reason that you want to use Bidler or something like that, because you don't want to test these things in a real network.
And where do you define like the connection to the network? You have like some kind of property file.
Yeah, yeah. There is a config file that has everything that you need. We are not gonna go through that because it's a lot of data and it's already set up for you. But going back to this, so Paul has a deploy function that will take the same arguments that the constructor. So here we have to pass it the name of the poll, right? So we just do that from JavaScript. And what we're gonna test is that the actual name is used in the smart contract. And how do we do this? It's just by getting the name from the contract and comparing it with a known value. So we can get the name by doing just poll.name. So this poll object is going to have the same functions that the Solidity contact has, but in JavaScript. It's just like a one-to-one model between Solidity and JavaScript that is very handy to test these things. Also, the good thing of doing the test in JavaScript is that you can reuse that code on the front end of your application. So here we use chai just like for convenience to be equal poll number 1. In a way?
Do you need a wait on that last line?
No, not really, because we already have one here.
As in, yeah, so you need that wait.
Why do I need?
Yeah, the await there.
Because name is an async function because it has to go to the blockchain, ask for it to execute the name getter, and then when that value returns, the promise that this name represents resolves or something like that. I mean, async functions are a little bit hard in JavaScript, but most of the times when you call a function in a smart contract, you need an await. OK, I'm going to add this dot only here, so we are only going to run this test.
Is anyone lost? Is everyone following along?
Where is this test located? Is this in the test folder?
Yeah.
Okay.
I just created an example JS thing.
And what NPX command are you running?
What's NPX?
What NPX command are you running?
Yeah, NPX Bidler test.
If node running locally.
Well, Bidler starts its own node right before running the test and stops. No, it's called Bidler EVM. It's like an alternative to Ganache with some smart contract debugging functionality. That's what I'm going to show next. Yeah. Yeah, so you can go to its website here. There's like a section of useful links, and there's the Bidler documentation. But in general, if you clone this repository and read the README, you'll get a much better understanding than now, because we have a very short time to explain a lot of things. But you should be able to clone this repository and use it as the base boilerplate for your project, just by reading the README and a little bit of the test files, a little bit of the contracts, and there's also like a tiny front end that you can use to base your front ends. OK, so if we go back here, what we are doing is deploying a poll with a given name, and then getting this name and comparing to the same value that we passed. And as everything is going OK, we are just getting a contract passing. But what we want to show you is how to debug contracts, because that can be a very frustrating experience. And for this, I'm just going to break this contract on purpose. How do we do this? Do you want me to go back to? Yeah, it's fine. Here?
Yeah. She's making a phone.
The front end just connects ethers to like a live blockchain that's running locally. Like to run that one, you can do npx Bidler node, and this starts like a yeah, like a local ganache thing with some debugging output enabled like here. I mean, it's not receiving any transaction, but you'll get some interesting output. And then you can point your MetaMask or whatever wallet you want to that. Yep. All these things are explained there. So okay, let's break this smart contract. The easiest way to do this is just to add a revert function call. Just like this will make the transaction fail and everything reverts. And let's do that. So what's going to happen is that this line that is trying to deploy the contract is going to fail. So when we run our tests, we should see an error there. And so we see like this test on red. That's because it failed. And the interesting part is that here you have a stack trace of Solidity embedded in a JavaScript exception. So Mocha will know how to show that. And that's what Viddler VM does. Whenever you execute a contract, it knows which contract it's executing. It's not just like blindly executing opcodes. And it can show you exactly where your test failed. Yeah. So if one of your tests fails, you just have to go there and figure out why. Of course, it's here because we just studied it. Yep.
So your runner stopped. It didn't run any further tests. So it's
yeah, that's because I did this only here, just to make things faster. Also, we can pass revert a string. Which will be available in the error message, but it's not very useful. There's no things like string concatenation in Solidity, so we can do things like this. This doesn't exist in Solidity. And the reason why they don't exist is because these are quite expensive operations. Like string operations can get expensive pretty fast. Like if a string is to be concatenating two of them, we run out of gas. So revert reasons are cool, but not so much. Like you'll only get like a fixed revert reason. They are good for testing. You can do things like making sure that a transaction actually meets the revert reason that you want. Like we could test for this string, and that's something very common. There are many examples of this in the actual test of the Paul contract in this repository. But for now, let's just run it like this. So instead of saying transaction revert without reason, we should get a better error. Oops. OK, so now we get this kind of weird error message that says, VM exception while processing transaction and the revert reason. But you still get the Solidity stack trace. Here it's just a single frame because it's only the constructor, but you'll get the entire stack trace. But still, this is useful to figure out which line of the contract failed, but not why. So because you can actually output values from there. So one of the things that Viddler has is console log, just like JavaScript. For use it, you just have to import this contract that it's called nomic-labs-viddler-console log. And then just call it like if it were JavaScript. So we could do something like console log deploying the poll with name, and get values out of the contract. So this is how you can figure or try to figure out why your contract is failing, which is kind of the same that you do in JavaScript or any other language. You just output parts of the state of the program to,
Is there a way to debug smart contract in a way that like stops and I go like one line after another?
You can do that in Remix, like the previous thing that we saw, but not in Beadler. Right. So for now, the tools that you have for debugging are console log and stack traces. So if we rerun this test with the console log on it, you should see it here. So deploying the poll with name, poll number 1. Yeah.
Is there any reason why you can't go line using the
Can you repeat?
Is there any reason why you can't go line using the
Because we still have to implement that. Yeah, that's like a ton of work, especially like things like decoding the state can be extremely hard, and we haven't had enough time to implement it now, mostly because we were trying to get the basics working. Things like stack traces and console log weren't the thing before Beadler, and we just recently launched these things.
No, it's awesome. I think it would help so much.
Yeah. And then the other thing that you can use to debug your transactions is to enable like a very verbose Beadler mode. So to do this, you have to go to beadler.config.js, which has a ton of things, but we can ignore most of them for now. And there, yeah.
About the console log.
Yeah.
You mean there is a real contract console deployed on the real blockchain, or is it used only for testing?
Everything here is on a real blockchain. It's like a simulated blockchain that Beadler starts and stops automatically. But yes, there is a console contract. It's not exactly a contract, it's a Solidity library. Those are treated a little bit differently. But yes, you can actually go to the console contract like this, and you won't understand a thing, because this is a little bit of EVM magic. It's not like actually printing anything. It's Beadler that detects these things and print them. But everything in a smart contract is written in Solidity, yes. So going back to the verbose output that you can enable, you just have to go to the config. Here, most of the data of the config is in this module exports object. And here we have network configuration. It's like a section of the network. And Beadler EVM is the one we are using. It's like this special automatic network. And here we can do something like login enable true. And when we run the test, we are going to get lots of output for every transaction and call that we do. So instead of just seeing the JavaScript execution of the test, we are also going to be able to trace every transaction and call. OK, so do you need more time? OK. So if we rerun this, you're going to see a trace of every call into the blockchain. So first, we do this call ETH account to get the actual accounts that the node has. Then this net version, we can ignore it. It's just like an internal Ether thing to figure out how to set itself up properly. And then we have this ETH estimate gas. What is going on here is that Ether is trying to make a transaction, but it has to know how much gas to use. And it does it by calling this ETH gas method of the node, which will run or simulate the transaction, figure out how much gas it takes to run it, and then maybe improve that approximation a little bit to be sure that it's not going to fail, and return that number. But as our constructor method is always failing, the if send transaction is also failing, because when the node tries to simulate this transaction, it will fail, and we are gonna see this here. So what you get is the name of the contract that is being deployed, who is sending that transaction, how many ETH that transaction has. In this case, it's just 0. The console log, any call to console log will be displayed, and also the Solidity stack trace.
The constructor is only called when creating the not at every transaction, right?
Right. So if we change the contract and to make it stop failing, and we rerun the test, it's gonna pass, and we are gonna see the other things. So here, estimate gas was successful. Then Ethers made the ETH send transaction, pretty much the same one, but here it used some gas, and it was mined in a block. And then there's a bunch of things that Ethers does to actually confirm that the transaction has run successfully. And then finally, there's this ETH call that it's gonna call Paul name, like the function name of Paul. And you get some data like who sent it and which was the Paul contract. And that's it. If you add more things like another call to Paul name or a call to another function, you are gonna see more ETH calls or ETH send transactions, depending on whether if it changed the state or not of the contract. So if you are calling to a function that changes the state of the contract, Ethers will know that it has to send a transaction, and that's what it's gonna do. If it doesn't change the contract, it's gonna do a call. That is what Patrick explained, of running a transaction locally and returning the return data of that simulated transaction. Yep.
Can we specify like a different address for the call to Paul name, because it's using the creator to do that query? So if we wanted to use like a different address.
Yeah, sure. You can do that.
That's how we can do an example.
Yeah. So to do that, you are going to use the connect method of Ethers. Here you can pass it, I think, an address or what Ethers call a signer. Signers are Ethers abstraction for accounts, but we first have to get them. So we can do this, or signers. And then do something like signer 1.
Cool.
Let's rerun it. Did it save it? Yeah. Oops. Thanks. So, yeah, it was sent from this and from this. Right. So things like this are explained on the README. So if you want to go to the details of how to do all these things and many more, you can read that. So any questions so far? Ya no hay más tiempo, ¿no? Yeah.
So how does the gas estimation work? Does it actually run it against the blockchain and then checks it out how much of the gas was used?
Yeah, it's like a binary search of gas. Like you first run with a random value the transaction, like a simulated, not like actually run the transaction, and see if it fails. If it fails, increase the gas. If it fails, increase it. If it passed, try a little bit lower gas. And just like that, yeah. I mean, you could do something clever or more clever, but it's better to be sure that you are gonna get a right estimation than doing it faster.
As I understood, like every operation has a pre-specified gas cost, right?
Yeah.
So you could just parse it a bit like a syntax tree.
Yeah, the thing is that you are gonna have like different contour flows for every transaction depending on the actual state of the contract. So let's say that you have an if state variable equals 1. Yeah, so it's gonna depend on the state, which is an actual problem even for production applications, because sometimes if your contract is being used like a lot, and you may run into the situation where a gas estimation is not correct for the time where your transaction gets mined. Like you may estimate the gas, do this dry run of the transaction, and then the state of the contract changes before your transaction gets mined because of another transaction getting mined before it. And that can be a real problem. So what you normally do is multiply the gas estimation by like I don't know, 10% more or something like that. But most libraries like Beadler or other frameworks already do that for you.
What happens when you specify a gas amount that is sufficient, but the gas price wouldn't be like high enough? When you wait in that,
you may wait for a very long time. Yeah. So one of the reasons to use like a simulated testing network is that you can mine transactions immediately. So whenever EVM receives a transaction, it mines a new block. So you don't have to wait like forever for your test to run. You could actually run them against like even mainnet if you are willing to spend some money on them. But that's going to be super slow because you need to wait for transactions to be mined. So, okay, so we are running out of time. So I invite you to visit the repository if you haven't, and read through its README. It has sections explaining all of these things and more. Even things like setting up your Visual Studio Code, a proper explanation of ethers, or if you don't know how to work with mock and chai, there's also a 5 minutes tutorial. It's like just like an actual test with lots of explanations on what all these things are, why the script is there, why it's there, without being imported and things like that. And then after the ethers explanation, you are going to find other things installed, like Waffles Chai Matchers. This is a library that adds like very handy assertion functions to Chai. So you can test for things like revert reasons, or you can also test that a given event is emitted in your transaction, or its params and things like that. There's more info on how to debug the transactions. It's pretty much the same that I showed, but with more details. Some explanation on how to deploy your contacts, because so far we've been deploying them to Whittler EVM, but that network is both automatically created and destroyed. So this won't be useful for things like testing your front end or actually deploying it. But there's a script that will help you deploy it to a real network. There's a bunch of networks to try your smart contacts on. Whittler EVM can also be used like persistently. You just have to run npx Bidler node. This is going to start a JSON RPC server that every transactional library knows how to use. Every wallet and library knows how to use. But there's also a bunch of testing networks that are live and actually maintain and more realistic or similar to mainnet. Those are called Ropsten, Koban, Rinkeby, and Goldly. You can use pretty much any of these. All of them work. And here there's an explanation on how to use them. And finally, there's like a super simple front end built with React. It doesn't have much functionality. You just kind of get like an overview of the state of the poll and like very basic voting functionality. But it already has things like connecting your contract to the network, setting up ethers, and things like that can be very cumbersome to get right the first time. So take a look at it. I think all of it's contained in a single file. It has explanation for all the things that it does. And that's pretty much it. Enjoy the hackathon, join the Discord server. We are going to be there. There's a Bidler channel. You can make any question that you want about Bidler in general or about this tutorial. So feel free to join and ask whatever you want. Thank you.